here we have extended the ruggedized lens version with water protection. Here is O-ring sealing behind the lens, which is on the flange on the camera to protect it from intrusion of water. These lenses basically are made to be ruggedized with gluing each single lens inside. And here is in addition O-ring sealing for water protection. That is enough for spray water. It is, the application is, for example, if you are somewhere where you have to water flowers and you have the camera in between, or you have some moisture which condenses on the products, or you have to spray and clean the products in the room and you have a camera there, or the housing is too big and you need to reduce the size. So that's why this compact solution, which is waterproof, is recommended and needed. The lens is basically a superb measuring instrument. It has no move of optical axis by construction. The optical axis is totally fixed because the construction is like a pipe. There's no moving element inside which makes the optical axis stable if you turn it around or if you swing it around. So this is a very stable construction for even high precision measurement. We have here another camera in application. This is a sphere camera. These are very modern sensors. They are able to see visible light and sphere. This is very new. Before you used for visible cameras silicon sensors, which sensitivity ends about 1100 nanometer. And for sphere application, you use cameras which are sensitive from 900 to 1700. And this is now two cameras, is fusion in one. It's sensitive from 400 to 1700, and you can just illuminate with different wavelengths and see the picture and reflections of the object depending on the wavelengths you apply. And the idea of the requirements for the lenses are that we don't lose the focus. Usually the lenses are made for a certain wavelength bandwidth where the focus is stable. But this is an extended, we can say, construction for extended wavelengths application. From 400 to 1700 nanometer, 2000 nanometer with stable focus. And here, for example, you can see this is the visible light. This is sugar, and this is salt. And changing the wavelengths, you can see this is visible light, and this is sphere wavelengths. Visible light is just the bulb. It has a wavelength from 400 to like 800, 700 nanometer. IR is starting from 780 plus. And this is the wavelength 1500. It's a LED, so it's a very narrow bandwidth in 1500 nanometer. So you can sort products by using different wavelengths. You can here, from the same axis, from the same perspective, illuminate with visible light, color, IR, sphere, and you can page through all wavelengths and see what is the response of your object. This makes the analysis and sorting effect or sorting result much more flexible. Yeah? And you have no perspective. Usually you have a visible camera from one side, a sphere camera from the other side. If you look from two different perspectives, you don't have the same reflective from the surface. But here it is exactly the same axis, you can really compare. So this makes this application very new. You can look deeper in skin for vein observation in medical application. You can see teeth, you can see food, water content of plant. You can see where's damage is it the right plant, where do I have to water the plant, where is it too much, where is it too little. So you can really use food, vegetation, medical application. You can even see military application. You can see a laser beam, targeting laser. You can see it through fog. So many applications can be covered by this kind of technology.
Okay. Thank you very much.
You're welcome.